It seemed that Einstein worked for the best part of a decade trying to resolve how Newton's worldview squared with Maxwell's worldview, and vice versa. On a certain day in May 1905, Einstein had a long discussion concerning the matter with his confidant, Michel Bessot, at the end of which Einstein essentially surrendered, deriding himself for having failed, and announced that he was to be done with the problem. But later that evening, after he had returned to his apartment, the Bern clock tolled, and that put him in mind of the streetcar that ran near it. All of a sudden, he is imagining the streetcar to be leaving the clock tower at light speed, Einstein riding along with it. He notices his wristwatch is running properly, but the Bern clock has stopped. It is here that the idea of clocks running at different speeds broke like a storm in his mind. And working assiduously, he finished a paper that introduced special relativity just 6 weeks later. Our project here is to look doubly hard at his first impression of the clock and the streetcar. And as we have noted Cartesian artifacts throughout this discussion, it is critical that we note how completely Cartesian this first impression really is. Without any reference to the ether, and without discounting it, Einstein produces a completely common time rate scenario in this construction of a racing streetcar and a frozen clock. The light leaving the clock can be described as an entity having a rate through space. The streetcar can be described as an entity having a rate through space. They are both traveling the same direction, which is germane to their integration with one another. The information carried by the light beam as Einstein achieves light speed alights on his eyes, and no other can catch up. If that light is carrying information indicating it is 12 p.m., in other words, noon, then the clock will freeze at noon and never report even 1 second after. Newton, Galileo, Descartes all understand this outcome perfectly. Were Einstein to slow the streetcar, Bern clock would slowly begin to move, and by the time the streetcar found itself at rest, both clock and wristwatch are keeping the same time. In his seminal paper, Einstein works out that the Bern clock is subject to a classic time rate expression. It slows with respect to his wristwatch by t divided by the square root of 1 minus u squared over c squared. This is correct and reasonable. But to solve his larger Maxwellian problem, he must witness all clocks in the universe to stop while he is at light speed on the streetcar. Thus, an observer moving at c perceives himself in a perfectly normal state. This makes Maxwell happy. Said observer witnesses all other clocks to have stopped. Maxwell shrugs and says, Einstein comforts him and reports that all clocks have their own timekeeping, and that makes Maxwell's equations work because each is in its own relative rest state. Maxwell is happy again. Newton, astonished, walks off the playing field. Einstein shrugs. I only went where the empirical thinking led me. With this passion play ended, we are here to complete the Bern clock scenario using Einstein's first impression, which was completely Cartesian. It is an important exercise and helps support the thinking in Michelson's error. Which brings us to Einstein on the speeding streetcar experiencing a frozen Bern clock. His experience, as we've noted, exists because light carrying its information from the clock is flowing through space at the same rate and in the same direction as he is on the streetcar. The Bern clock cannot update. So here we see it. We see the basic setup for a Bern clock Redux. Except in this case, we're going to have a Bern clock South station and a Bern clock North station. And what we're going to find is that they are separated by 10 light minutes. And along the way, at every 1 light minute mark, we have motion activated street lamps that will indicate the passage of any entity moving along the track. We're going to look at this setup as if the streetcar were traveling very, very near the speed of light, or let's accept that it is at the speed of light. So let's put Einstein and his streetcar in motion, watching as he travels from Bern Clock South Station towards Bern Clock North Station. Here he goes. Halfway there already. And finally he gets to Bern Clock North Station. Now let's pull back and reassess. If we're saying that he's moving at the speed of light as he passes Bern Clock South Station, then sure enough, he finds himself seeing that Bern Clock South reports its time as 12 o'clock noon. 12 o'clock noon as Einstein passes right here. And it will report that time for the continuation of his journey, all the way through to Bern Clock North Station. He is simply traveling with the wavefront that has, like a snapshot, only one collection of information in it. And as he looks back, he sees the Bern Clock South Station only reporting noon. It never changes. So he travels 10 light minutes from the Bern Clock South Station to the Bern Clock North Station. And all he ever sees from the South Station clock is it reporting 12 noon. Now we notice there's a clock keeper at Bern Clock South Station. And he, of course, sees Einstein and the streetcar pass and disappear into the distance. And exactly 2 minutes later, as registered by the clock above his head, he sees a flash from the first motion-activated street lamp Einstein triggers as he passes. It has flashed and sent a signal back to the South Station. Well, okay, it took Einstein a minute to get there, and then it's going to take a light minute for the flash to get back. So for his local time, the clock keeper sees Bern Clock South reporting 12:02 when the signal from the first street lamp gets back to him. And guess what is globally true from the Cartesian argument? Well, it's globally true from the Cartesian argument regulating the scenario that Einstein would in fact be at that instant 2 light minutes away. And here's the conservancy of the argument. From now on, as Einstein triggers, each street lamp light goes back towards South Station as he travels toward North Station, both at the same rate. And so now the clock keeper at South Station will see a flash every 2 minutes, and he will see the 10th flash at 20 minutes after noon. After all, it took Einstein 10 minutes to get there to the North Station, and light 10 minutes to get back to him. Einstein's journey to North Station took 10 minutes, and the incremental reporting took 20 minutes. The clock keeper, good at his Cartesian analysis, knows Einstein is in fact 20 minutes down the line when the flash from the North Station arrives, simply confirming that he made the 10-minute journey on time, assuming he was to arrive at North Station at 10 after the hour. Now we know Einstein will only see the South Station clock reporting 12 noon for the entire journey. But what does Einstein see as he trains his telescope on Bern Clock North Station? Well, the instant he leaves Bern Clock South Station, he begins to spy on Bern Clock North Station. What does he see? Well, he sees light that has traveled 10 minutes to get to this point in space he occupies beneath Bern Clock South. So he sees Bern Clock North reporting 10 minutes to midday, even though he's passing through South Station that's reporting exactly noon. Assuming they are properly synchronized, he understands that it took 10 minutes for light to get to his current point in space, so he's not lost. He says, "Oh, the clocks are very well coordinated here." And so it goes. As he gets to the first street lamp, 2 minutes have elapsed on the clock at Bern North. Obviously, as light made its way to Bern South from Bern North, Einstein made his way to Bern North at the same rate. And so it goes. For each street lamp he encounters, 2 more minutes have lapsed on Bern Clock North. As Einstein reaches the fifth street lamp on his journey, the Bern Clock North reads 12 noon. And when he gets to Bern Clock North Station, it reads 10 minutes after noon. So what is Einstein to make of his collected data? One clock reports 0 time has elapsed. The other reports that 20 minutes have elapsed. If Einstein is allowed to understand that the light traveling with him from Bern Clock South was passing each street lamp at C, and he also knows the distance between the two stations, then first order deduction would tell him that 10 light minutes passed as he went from South Station to North Station. He was traveling at C, and space conserved the integrating behaviors, as it should if energy is to dissipate in accordance with the inverse square law. Of course, the South Tower keeper, now aware of Einstein's paper, observed Einstein to be moving at c, and applying the relativistic operator t divided by the square root of 1 minus u squared over c squared, he is certain that time has stopped for Einstein. What we have been exploring in the Bern clock redux are the issues that seem to supercirculate when one considers very simple time rate scenarios that must be overlain by special relativity and relative rest. Consider Einstein on his way to Bern Clock North. As he passes a street lamp, light leaves it at C, which overtly leaves Einstein to be separating from that wavefront at 2C. Now watch the fandango that occurs, which Lorentz supposedly fixed. Conveniently, Einstein, at his uniform velocity, can't know he is moving. He is at relative rest to the scenario. For him, all other entities possess motion. He, therefore, is allowed to apply his special math operators to any such entities. For Einstein, the clock keeper's time at Bern South has slowed by t divided by the square root of 1 minus u squared divided by c squared, which effectively means it has slowed to 0. Also applicable to the clock keeper is the contraction of length. When Einstein applies L times the square root of 1 minus u squared over c squared to the clock keeper's frame, it also shrinks to 0. Now we must be careful. This contraction applies to the dimension along which the frame, meaning the clock tower, is moving. Of course, it is moving straight away from Einstein, so it shrinks down to one thin film. There is no depth of field for the clock tower. It is worth recalling Einstein's original impression of the clock stopping and noting that no information will update due zero differential velocity between light and streetcar. What we must keep uppermost in our minds is the fact that, forget the hands, no other information will update. By proper Cartesian reasoning, Einstein understands, assuming he achieves light speed just as he passes Bern clock south striking noon, that image will never update, meaning the Bern clock tower will never recede into the distance. That snapshot of information will lie gently, unchanged forever, as a film upon his eyes. It seems he took the next 6 weeks to concoct the math that would define this film resting on his eyes. Its time shrunk to zero, and its depth of field shrunk to zero. What we're attempting to say is that he might have consulted Bern clock north in the middle of his cogitations. It can be said that the Bern clock north is approaching him at sea, and maybe one could apply Einstein's operators to the tower. But space is impregnated with information that forces the clock's manifestation to update itself in Einstein's frame. Einstein would perceive the north clock as running, not normal to his local time, but hypernormally. And of course, Bern clock north depth of field could not be forced to zero by the length contraction. Einstein could easily perceive a bird flying behind the clock and a bird flying behind that one, and so on. As time updates, so does depth of field. Again, I am only one who thinks relative rest blinders an otherwise sentient creature, meaning we humans. In Michelson's error, I try to show how such a creature might reason through and then build a device that thwarts this blindness. I am only hopeful that the good listener will go on to entertain Michelson's error with the thought that some of this Cartesian thinking has merit. Thank you.